Magnetism follows along very closely to the things that we did when we were solving for electric fields from charge distributions. A lot of the path integrals we're doing over current lines to find the magnetic fields are very similar to the integrals we did over charge distributions to find electric fields. And then we said under certain symmetries, we could use this special equation called Gauss's law that helped us find the electric fields very quickly and easily. There's actually something similar for magnetic fields. It's called Ampere's law. Ampere's law is written this way. The integral of B dot ds around a closed loop is equal to mu naught times the current enclosed by that loop. Now there's some subtleties here that make it a little tricky. Remember with Gauss's law, we said Gauss's law was always correct. It just wasn't very helpful in a lot of situations. It was only helpful when we had really nice symmetry, and the integrals in solving Gauss's law was easier to do than integrating over the charge distribution to find the electric field. In this case, Ampere's law is not always correct. Maxwell realized that, and he added another term to this equation, and that's known as the Ampere-Maxwell law. And we'll talk about that in a future chapter. But this case, Ampere's law, is good for certain situations also. It's good for infinitely long straight wires and for ideal solenoids and toroids. First, let's do a really simple check to make sure this is correct for a very simple case, an infinitely long straight wire carrying a current. Let's situate our infinitely long wire perpendicular to the plane of the page, with the current coming out of the page. This will form magnetic fields that encircle the wire. And what direction is that magnetic field? Using our right-hand rule, it would be in the counterclockwise direction. So if we want to use that as our path, remember this circle here means that this integral is around a closed path. So let's pick a circular path around our wire. And along this circular path, the red dashed line, we're going to take that as our circular path. Along that circular path, we know the magnetic field is constant. And it's going to point in the same direction as our ds. ds is just a length element along this path. So they point in the same direction, so the dot product can go away. The cosine of 0 degrees is 1. And I've got the integral of b times ds. b is constant along that circular path, around that wire. It comes out of the integral. And the integral of ds is just s, the arc length or the path length around this circular path. And the path length around a circle is just 2 pi r. So what do we mean by I enclosed? That is the current enclosed by this path that's defining our path integral. So in this case, the red dashed line is our path. So the current enclosed is just the current in our wire. So the magnetic field at some point around an infinitely long, straight, current-carrying wire is mu naught I over 2 pi r. And we found that already using the Biot-Savart law, so that checks out. We know that that's true. So we just checked Ampere's law for this special case, an infinitely long straight current carrying wire. There are other cases where it works very nicely also. Solenoids and toroids. We'll talk about those in a minute. Ampere's law does not work if this wire is not infinitely long. So the fact that it's infinitely long makes it acceptable to use Ampere's law. If it's not infinitely long, there are issues with the current density changing, and that means we have to use the Ampere-Maxwell law. It also isn't helpful if this wire is curved. I believe Ampere's law would still work with an infinitely long curved wire, but it wouldn't be helpful. You wouldn't be able to find a path around the wire where the integral of b dot ds is easy to do. So if you remember, infinitely long straight wires is one of the applications for using this, and you can see how quick and easy it is. Students often ask me, every time I see an infinite wire on the exam, do I need to go through and calculate with Biot-Savart law and fill up, all those integrals and minus infinity to plus infinity using Biot-Savart law to get the magnetic field? And I say, no, you can use Ampere's law, and in a couple of lines, you can get the magnetic field from that wire. So let's do it one more time. On the exam, you see an infinite wire. Here's our situation. We're going to go around this red path, the circular path, centered on our infinitely long straight current carrying wire. We know that b dot ds, because my magnetic field points in that direction, and I'm going to go around that wire in the same direction. My ds will also point in that direction. So b dot ds just becomes b ds. I enclosed is just the current in my wire. This is b is constant. It comes out of the integral. The integral of ds is just the total path length, which is the perimeter of my circle, 2 pi r. And there's our magnetic field from an infinitely long straight wire. One place where Ampere's law is useful is finding the magnetic field inside of that infinitely long current carrying wire. So I've drawn the cross section of the wire, and let's say it's carrying a current I in this direction. If we look at the end of the wire, that current is coming toward us. Let's take the case where the current is uniformly distributed over the cross section of the wire. Now we've already found the magnetic field outside of the wire for our point of interest, r, greater than the radius of our wire. We know the answer to that. We've just found it. Now we want to find the magnetic field inside. So our path length, our Ampere's path, is going to be inside of the wire, this red line. So the left side of this equation is the same whether we're inside the wire or outside of the wire, because anywhere along a circular path, if we pick a circular path centered on the wire, the magnetic field dot ds just gives us the integral of b ds. B is constant. The integral of ds is 2 pi r. What's different is ion closed. Let's figure out how much of this current is inside of our red circle. So we have a certain amount of current flowing down this wire, and it's uniformly distributed over the cross-sectional area of our wire. And we want to know how much of that current is enclosed or is inside of the red circle, our path integral. Where I is the total current flowing in the wire. So the magnetic field is proportional to R inside of the wire. If we were to plot that, we could plot it. Here's our wire. That's the radius of the wire. So between 0 and the radius of the wire, the magnetic field increases linearly. B is proportional to R. It's linear in this region of space. Then it drops off as 1 over R as we move away. So we've talked about using Ampere's law for an infinitely long, straight, current-carrying wire, both looking at the magnetic fields outside of the wire and inside of the wire. Now let's take a look at another application, solenoids. A solenoid is just a coil of wire. I don't know why we have so many names for it. We can call it a coil, we can call it a solenoid. In another couple of weeks we'll be calling it an inductor, but it's just a coil of wire. And I could draw that like this, but it's a little hard to see exactly what's happening when I draw it like that. So we tend to draw it like this. We draw the cross section. If I was to slice that coil right down the middle and open it up and look at the cross section, I would see a bunch of wires that look like this. And the current would be coming out on one side and wrapping around and going in on the other side, and then coming out over here and going in over there. You get the idea. Coiling around and around, something like that. And each one of these wires has magnetic field lines circling it. So I could draw magnetic field lines that go around this wire and this wire, and similarly on this side. And in the middle here, we'd have one that goes down the center, and maybe something that kind of forms we were getting magnetic field lines encircling all of these wires. And what happens as we squeeze these coils closer and closer and closer together, the magnetic field outside becomes weaker because these lines become farther apart. As those coils get closer and closer together, the magnetic field outside becomes weaker and weaker, and the magnetic field on the inside becomes more and more uniform. And eventually we get to the point where we call it an ideal solenoid. For an ideal solenoid, these coils are packed very, very densely, very tightly together. And our current would be coming up on the wire on the right, circling around, going in on the one on the left, coming up on the one on the right, in on the one on the left, around and around the coil. Outside, we would have no magnetic field. And inside, those magnetic field lines would become nice and parallel. It would become uniform. We would have a constant magnetic field inside. It doesn't matter if you're at the center or if you're standing right next to the edge. The magnetic field is the same everywhere inside an ideal solenoid. So how do we approach an ideal solenoid? The turns have to be very close together. Those wires have to be packed very tightly, very close together. And it has to be long. Ideal solenoid would be infinitely long, but we know we can't make an infinitely long solenoid, so we say the length has to be much greater than the radius. And if we can do those things, if we can get the turns packed really, really tightly, close together, and we can make it long compared to its radius, then what do we get? We get a nice, uniform, constant magnetic field inside the solenoid, and we get no magnetic field outside. I told you an ideal solenoid was a case where we could use Ampere's law. So let's do that. Let's find the magnetic field inside of an ideal solenoid using Ampere's law. Here's my solenoid. Has a nice uniform magnetic field inside of it, no magnetic field outside, and I've drawn this red rectangular box. That's my path for Ampere's law. So the integral around this whole closed path of b dot ds is equal to mu naught I enclosed by that path. Well, let me number the sides. I'm going to break this up. I've got side 1. I'm going to call this little section here 2, and out here 3, 4, 5, and then this little section here I'm going to call 6. That means I can break this up into 6 integrals. The integral of b dot ds over side 1 plus the integral over side 2. And I have to do that for all 6 sides. So let's look at each one of these, starting with side 1. B is constant everywhere along side 1. And my ds is going to point in the same direction as B. So I just get the magnetic field times the integral of ds. That's just the length of the wire, which is L. So for side 1, B is constant, and I get B times L. For side 2, that's this side right here, my magnetic field points toward the bottom of the page. I'm going to go around my loop in the counterclockwise direction, so ds would point to the right. ds points to the right, magnetic field points down. They are 90 degrees apart, so the cosine is 0. The dot product yields 0. For length 2, B is perpendicular to ds, so we get 0 for that side. For length 3, b is equal to 0 everywhere outside. So the integral of 0 around the path is 0. For side 4, b is equal to 0. The integral of b dot ds along length 4 is 0. For side 5, b is equal to 0. The integral of b dot ds is therefore 0. And for side 6, we're similar to 2. We know that b is perpendicular to ds, so we get the dot product, or it gives us 0. Cosine of 90 degrees is 0. That gives me this formula. And I need to figure out what I enclosed is. So I come back up here, I look at my picture, and I see that I've enclosed a certain number of turns there inside of my loop. I'm just going to call it capital N. The number of turns times the current. So the number of turns multiplied by the current in each one of those turns gives me the total current enclosed by my loop. And I divide both sides by L. And the number of turns per unit length is usually a constant for a solenoid. Once you start winding the turns on that cylinder, you get the same number of turns per unit length the whole way down the cylinder. So this is usually a number that's given for a solenoid. And we write that as lowercase n. And there's our magnetic field inside of an ideal solenoid. Mu naught, our constant, multiplied by the number of turns per unit length for that solenoid, multiplied by the current.